Hello, everyone. Can you hear me?
Yes.
Yep. Okay, cool. So a couple things. You probably know your quiz is graded. You have until Sunday to put in regrade requests. So I know quite a few students haven't looked at their quizzes on Gradescope. So yeah, 3 points maybe. I don't know. And also, I guess your next quiz is on Tuesday. So yes. Any questions before we start?
I have a question.
Yeah.
Will we be going over the practice quiz? Because I have some questions on that.
I guess we can do that if we have time. Yeah. Oh, let me start my screen. You can see my screen?
Yep.
Yeah.
Okay. This isn't from the practice quiz, is it, James?
No, these ones are.
Okay. So if you want to go over practice quizzes, you can go to office hours. And are we doing a review, James?
I didn't think we had one scheduled, but there'll be 4 hours of office hours on Monday.
Okay, cool. Thank you. So if that's it, we'll just start. So let's do the base case of this induction problem. So we're showing the n factorial is greater than 2 to the n for n greater than or equal to 4. Does anyone know what we should write for our base case?
Prove that it's true for n equals 4.
Okay, yep. And so we write 4 factorial, and then we use our definition of factorial. This is 4 times 3 times 2 times 1. That's equal to 24. And 24 is definitely greater than or equal to 16, which is equal to 2 to the 4. So we showed our base case. And then need to write our induction hypothesis. And what do we put there? You can also write in chat.
Assume P of n is true.
Yeah, so P of n greater than or equal to 4. So we're assuming this. And then finally, you do your inductive step. And I'll give you maybe 1 or 2 minutes to do that.
And then maybe first the problem statement right before the base case.
Problem statement.
Where you define what P of n is.
Oh, okay, yeah. Yeah. Oh, yeah. Yeah, so someone said if it's greater than or equals. In this case, it doesn't matter, but I'm going to erase it anyway.
I have a question.
Yeah.
So for the problem statement, would we do something like let s of n equal n factorial and let maybe like k of n equal 2 to the n? And so the problem statement would be s of n is greater than k of n.
Yeah, you could do that. I mean, it seems like extra writing, but should be fine.
Oh, because I saw something similar on the practice quiz, like they assign different variables.
I mean, I wouldn't mark you down for doing that.
Okay, thank you.
Okay, so someone's seen the professors do both, so whatever you prefer. Has anyone solved it? Or at least have part of it done?
How about prove the, well, sorry. How about prove n plus 1 is like greater than the 2 power of n plus 1?
Oh, yeah. So we need to do that. We need to first write what we're doing. So we're showing p of n plus 1. Assuming. So you're doing this for p of n plus 1, right?
Yeah.
Okay. So you have n plus 1 factorial. And then you write this out.
Is equal to n factorial times n plus 1.
Yep.
Well, and for the 2 power of n plus 1 is equal to 2 times 2 power n.
Yeah. So we have over here 2 times 2 to the n.
Yeah, since the n's factorial is bigger than, we already assume like n factorial is bigger than 2 power of n, and n is greater or equal to 4. So the n plus 1 is greater than 1. So
yeah,
that is,
Yeah, so to put that together, by our induction hypothesis, n factorial is greater than 2 to the n. Why do I have that there? Okay. So we have 2 to the n times n plus 1. This is by induction hypothesis. And this, so we have n plus 1 here. Since n is greater than 4 or equal to, this is greater than or equal to 2. So we can say this is greater than, 2 to the n times 2. So this and this are because n is greater than or equal to 4. Does that make sense? Yep.
Yeah, it makes sense.
Yep. And so then we move to. So this one is a pigeonhole principle problem. And so we're finding the fewest number of times we need to roll a standard 6-sided die before we can be assured that at least 10 of the rolls result in the same number. I'm getting things in chat. Okay. Still confused. Are you still confused? Jerica?
But yeah, I think a couple people are confused about the previous problem, like how you reach the conclusion.
Okay. So if you're not confused, you can work on the pigeonhole one. So which step is causing confusion?
So when, like the last bit, when you say something like greater than 2 to the n times 2.
Oh, okay. That's just because of the way it was written here, so that it matches up, right? You know, this is here. Does that make sense?
Wait.
So we have 2 to the n times n plus 1. And this right here is greater than 2 because n is greater than or equal to 4, right? So this is at least 5. So we can say this is greater than 2 to the n times 2. Does that make sense?
I'm still confused of like where you got the 2 to the n to like in parentheses n plus 1, where you got from where you got to that point.
Yeah, okay. So we have n plus 1 factorial. It's equal to n factorial times n plus 1. And by our induction hypothesis, we assumed that n factorial is greater than 2 to the n. So we apply that right here. And that gets us that n factorial times n plus 1 is greater than 2 to the n times n plus 1. So this is by our induction hypothesis. I see someone says they got it. Does that help? Following Intel inductive hypothesis. I'm going to go with that cleared up most of it. So can someone get me started on the pigeonhole pin? Okay, yeah, so Charlotte, 2 to the n times n plus 1 instead of it being the next step. Yes. Can someone get me started on this problem? So we have a 6-sided die, and we're wondering how many times we need to roll it to get it to 10. Okay, yeah. So Nathan writes, we have m plus 1 is equal to 10. So we want at least 10 of the things in one box. And we have 6 boxes. And so we have, this means m equals 9. So we can use our formula, n times m plus 1. And this is the number of items. And this is equal to 6 times 9 plus 1. That's equal to 55. And there's another way you can think about this. So 1, 2, 3. So we can count them in boxes. Like, it's a really weird way to count. So we can count them in boxes like this. And, so we can, in the worst case, we can put 9 here, 9 here, put 9 in each of them. And this is the most we can fit in here without having 10 in any one. And then if we put 1 in any of these, we'll have 10. And this is equal to, so we have 54 things in there. And that's where the +1 comes from. Does that make sense? Any questions? Nope. Okay, so this one we have a few sets, and we're supposed to list out the elements in A intersect B union C, where A is positive multiples of 4, Y is even perfect squares, and C are numbers whose square is less than 1,000. So I would recommend first writing down a few elements in A, B, and C. I'll give you maybe 2 minutes, 2 or 3 minutes to do that. Do most people have this? It's hard to now actually see everyone. Okay, can someone give me some elements of A? Yeah, so Brendan has the answer all done, but sort of, yes. So can someone give me a few elements of A? Yeah.
Like 16, 4, 8, 12, 16,
12, 16,
and 20.
20. Yeah, so Jacob White asks, what is a natural number? So this is equal to these numbers.
Oh.
Some math classes will say that 0's not there, but yeah, so that's what natural numbers are.
Mhm.
Does anyone, so what's in just like first 3 or 4 elements in B? Deverin asks, what's the difference between this and integers? The integers have the negatives of these. So it would be -4, -3, -2, -1, 0. Yeah. Yeah, Z plus. Well, Z not negative. Elements of B, 2, yep, 8, that's 16, yep, 18, 32, so 32 is 64, this is 36, so this would be corresponding to 2 squared, 4 squared, 6, 8 squared. And elements of Z or C, I'll just write these. And nope, not negative. So now we're asked to find elements that are in A and B or C. So intersect B or C. So it needs to be an A and it needs to be in either B or C. So let's just do 5. So 4 is in C. So we can say 4 is in there. 8 is in B. So that's in there. 12 is in this one, is in C, so we can write that one. 16 is in C as well. And 20 is. And did I skip one? No. Yeah, that's 5. Yes. So everything from 0 to 28 is in C. No, you don't need B technically for this one, but you know, we also would have 32 in this set. Is everyone good on that? I'm going to say yes.
Yes.
So we're going to use Venn diagrams to verify the set property, which is one of the absorption properties, which says that A intersect A union B is equal to A. And so you're doing Venn diagrams, make sure you always have this intersection. So I'll give you maybe a minute to do that yourself. looks like okay, that's been a minute. So what should I shade in first? Chad or all of A and B? Yep. And this, it corresponds to this union right here. So then next we do, we need to take care of this right here. So we just shade in the parts that are A, and we note that it's an intersection. So it's in both. And if we look at this, the parts that are covered by both of these statements, we get the original set A. Everyone get that? Yep. So this one's a little more tricky. We're going to have 3 sets here, A, B, and C. And we're going to use Venn diagrams to show that the A minus B union B minus C is contained in A minus C. And give you maybe 2 minutes to do that one. Yep. Okay. Does anyone want to say where I should start? Okay. So I'll just start with A minus B. Yep. So A minus B is everything in A that's not in B. So do this. And that's everything not in B. And then next, we'll do B minus C. And that's everything in B, not in C. And so finally we do the intersection. So the intersection is going to be this part right here. If we do the A minus C part right here, we get this set. Yeah, union. What did I say?
I think you said minus.
Oh, yeah. Yeah, so this union, thank you. Is what the left-hand side is. And then for the right-hand side, we have this shaded green portion of this. And is the left-hand side a subset of the right-hand side?
No.
No, it is not. And so the problem asks us to come up with a counterexample to this. And so does anyone have a counterexample? I'm going to show you how I come up with these. So just put a number in each of the overlapping region, or each of these regions. So we have A equals 1, 2, 4, and 5. B equals 2, 3, 5, and 6. And C equals 4, 5, 6, and 7. So A minus B, that's equal to 1, 4. So this set. And B minus C, that's equal to, so 2 is in B, but not in C. 3 is in B, but not in C. 5 and 6 are also in C. So, and then we have A minus C, and that's equal to 1, 2, and that's it. And we can see that this union here is not a subset over here. Because, for example, 3 is in the left-hand side, but not in the right-hand side. Does that make sense? I'm going to say that's good. How are we doing for time? 15 minutes left?
Yep.
Yep. Okay, so this one is asking us to find the power set of B and intersect C. I'll give you about a minute to do this on your own. Switch to red again. Okay, so let's start by writing what B intersect C is. And someone tell me that.
1, 2.
1, 2. Yep. And we found that by doing, so we look at first element of B and we see that it's in C. Second element of B, see that that's in C. Third element of B, that is not in C. So we can now write our power set of B and C. And does anyone want to help me with this?
Would the empty set be part of the power set?
Yep, it is part of the power set. If I can draw it. Yep. And then, so the power set is just the set of all subsets of this set. So, you know, the set with 1 in it is a subset. Set with 2 in it is also a subset. And the entire set is a subset of itself. So that's in there as well. One thing to do if you're doing these is to check the size of the set. So we see that there's 4 elements here. And so the original set had 2 elements, and you'll have 2 to the n elements in your power set. So we had 2 elements here, and we're expecting 4 here. So that checks out. Any questions on that? I'm going to say no. Yes, also sets won't be on your exam. So this is more interesting for your homework. So for this one, we're determining whether these statements are true or false, and if they're false, providing a counterexample. So for the first one, we have for all sets A, B, and C, if A is a subset of B, then A cross C is a subset of B cross C. And I'll just ask, does anyone know if this is true or false? Okay, Matthew says that it's true. And that's right. Does anyone have an explanation for why this might be true? So if we if we write down the definition of this, this is the set of, A1, C1, so on. And we know that A is in B. So, yeah. So each one of these A1s will be in B. So we know that these are also pairs in B cross C. Does that make sense? Yeah, and Mohammed says something similar. B is this. So this says for all sets A and B, A union B times A minus B is equal to A squared, or A cross A minus B cross A. I guess this is supposed to be like a geometric or algebraic identity. So is this true or false? Yep, it's false. That's correct. And does anyone have an example? I say no. So if we have A is equal to 1, set with 1, and B is equal to the set with 2, then A union B is equal to the set 1, 2, and A minus B is equal to 1, the set with 1 in it. So, and we have A squared, that's equal to, 1, 1, and B squared is equal to the set with the pair 2, 2 in it. So this part right here is equal to this one. Yes. And our left-hand side has the element 2, 1 in it. So these two cannot be equal. Yep. And C, yeah, one more thing about that. Usually for these problems, simple examples are better than complex ones. You usually will be able to find something easy. And for C, we have 3 sets A, B, and C, and we're asked if A cross B cross C with parentheses around B and C is equal to A cross B cross C with the parentheses around A cross B. And in the interest of time, I'll write this. So this is false, and we can use just A equals 1, the set of 1, B is equal to the set of 2, and C is equal to the set of 3. And so in A times B times C with the parentheses around the B and C, we'll have an element 1, and then parentheses around 2 and 3. And in the other one, we'll have an element with parentheses around 1 and 2. So these two are not equivalent. So this is not the same. Let me look ahead. Yeah, okay. I'll let you do this set cardinality on your own. Yeah, so to show that these questions are false, just give a counterexample and we'll show that it's false. So for this one, we have that if A union B is equal to B, then A union B, A unioned with B intersected with A complement is also equal to B. So I'll give you a little hint. We're going to start with A union B, A complement, and we're going to try to move it to this form. I think that's a typo. I'm not sure. I converted this from PDF. Yeah, I think it's just A complement, so it's A tick. So we're trying to show this show this side can be turned into A union B. I'll give you 1 more minute. Okay, can someone tell me where to start?
Start with the left-hand side, and I use the distribution.
Okay, so we do distributive, so we get A union B, intersect A union A complement, distributive, and then what do we do next?
Negation? Oh, that's what I use.
So we could do the negation rule. So we get A union B, intersect the universal set, and this is by the negation rule. So everything is either in A or not in A. That's one way to remember this. And then we do
Substituted with the info.
Yeah. Yeah, so we can use the fact that A union B equals B. So we can rewrite this as B intersect the universal set. This is a problem statement. And then finally,
Identity.
Identity. Yep. We apply the identity to get B. And that's by identity. Any questions on that? Yeah, and that takes us to time. Any questions generally?
I've got a quick question on that one, actually.
Yeah.
So if A union B is equal to B, does that just mean that A is B?
A union B is equal to B.
Equal to B. So like, could it be rewritten as just A is B then?
I suppose logically it would be equal to B, or no.
Wouldn't it?
So
Alright.
A union B. So A could just be a subset of B, right?
Right.
And then A union B.
Oh,
was-
okay, I got you.
Yeah. So A is a subset. You know, it's it definitely could be equal, but you know, this is
Okay, but
also
it could also
possible.
be a gotcha.
Yeah, it could be contained in but not equal. That. Any more questions? Yeah, some other things. So please make sure to match your page, your questions to the problem numbers in the quiz on Tuesday. Yeah, so Brendan asks, how did we use negation in the second to last one? So right here. So we have A union A complement. And if you look at negation, it says that that's equal to the universal set. So that's where that came from. Okay, yep, good.
I have a quick question about the quiz too.
Yeah.
So on the practice quiz, each problem specified which proof we should use.
Yes.
Be like that on the real quiz where it specifies which proof method?
It is not like that on the real quiz.
Okay, awesome. Thank you.
And it will be like that. Do we have to write substitute? Yeah, so I think Brendan's asking if we have to write this. Yes. So we're just using the problem told us that A union B equals B. Mohammed asks, how many questions will there be? Right now there's 6. I'm probably going to keep it there. It's either going to be 5 or 6, probably. Yep. Anything else? I think we need to. James is lecturing next, right?